Okay, thank you very much. So I will be following Jim's talk by drilling down more into improving NAMD performance on multi-GPU platforms. And so just to introduce what I'll be talking about with Jim's scaling results on Summit, we take a look at just comparing the Summit GPU performance with, say, Oak Ridge Titan GPUs. And so we notice that when comparing the same number of nodes running, we're getting a factor of 10 improvement. However, we can really think in terms of the GPU compute power, 1 volta being about 10 Keplers. And Summit has 6 voltas per node, so why isn't there another factor of 6? And well, the answer, of course, is that scaling to multiple GPUs is difficult. But, you know, we have some work on NAMD to really make good use of the GPUs. So I'd like to start by talking about NAMD's use of GPUs as co-processors and sort of give a historical perspective on this. Pointing out that NAMD has been developed for more than 20 years. It's been GPU accelerated for over 10 years. In fact, it was the first full-featured molecular dynamics code to adopt CUDA. And there is definitely a challenge posed by today's multi-GPU architectures. And so the question that we all need to think about is how can Charm++ really help us address these challenges? I don't really have solid answers. All I can do is sort of pose some of the difficulties that we've experienced. So when we're calculating molecular dynamics, the parallelism is limited to each time step. Basically, we take coordinates and we calculate forces, and then we update the coordinates, and we have to calculate these basically these time steps sequentially for billions of steps. And so what we get to really parallelize over is the force calculation, which turns out to be about 99% of the computational work. And then the coordinate updating, which is maybe only about 1% of the computational work. And the work of the forces is dominated by the non-bonded forces, those that are, they have a short range, they vanish beyond a cutoff distance. But we have some other contributions to the force calculation as well. And finally, the coordinate update involves calculating the numerical integration, the constraints, the thermostat, barostat, things of that nature. And so, of course, if you're going to apply GPU acceleration to something like this, you're going to first target the most expensive part. So within this context, of course, NAMD was already a scalable parallel program using a hybrid decomposition with Charm++. So similar to the diagram that Jim already showed you. But the idea is that not only do we have a spatial decomposition of atoms, we also have a decomposition of the work that's being calculated between these patches of atoms. And so for each patch of atoms, we actually have 27 interactions with its neighbors. And so that gives us a large amount of work then that we can go ahead and schedule for load balancing. And so this is what Charm++ enabled us to take advantage of. And so the way that a step works, again, I think Jim showed this identical slide, is that we have an integration step, and then we've got the force calculation that's done, and then we do the integration again. And of course, we were taking advantage of the GPU by offloading this non-bonded force calculation. And so the early non-bonded forces kernel was pretty remarkable. This was work by Jim. It was remarkable in that it managed to use all of the different parts of the GPU memory to maximum advantage. So it basically involved bringing in coordinates from a patch and then streaming coordinates from another patch. And so it used the constant memory cache for calculating what should be the excluded interactions, and then it also used the texture memory to do its force interpolation table lookup of some of the expensive parts of that calculation. But all in all, it ended up being quite effective for the very early GPUs. So this gave a notable performance boost. It was an 8x speed up for the non-bonded overall. Let's see. And so when you also included the PME calculation as well, the GPU maybe became equivalent to a quad-core CPU. And latency was further decreased by paying attention to the fact that our force calculation, we would need to schedule the remote forces first and do that calculation so that we could get those communicated off node as quickly as possible. And so when we paid attention to details like this, we had something that was fairly effective for the hardware of the day. And so just to recap, the advantages of this approach of treating the GPU as a coprocessor was that we were able to fit it into the existing parallelization of NAMD, and we were able to, most importantly, I think, extend the existing code without modifying the core data structures. And so this allowed us to really take advantage of the Kepler-based computers and get good scaling on these. So Jim showed similar scaling plots where the Kepler-based systems are performing quite nicely, the Blue Waters and Titan. So the challenge has come with the increasing difference in the computation rates between the GPUs and the CPU. And so in the generation of Pascal versus Haswell, we saw a 20x flop rate difference between the two. And in fact, to really achieve this bottom performance, it really requires full use of the CPU cores and vectorization. So the difference today is made even worse by having multiple GPUs per node on systems like AWS, DGX, and Summit. And our past efforts to balance work between GPU and CPU have been shown now to be CPU bound. So further work was done over the years to try and optimize the GPU code better, and also with the vision of the GPUs that were coming online with Maxwell and Pascal. And so some of the work that Jim did was to overlap GPU communication and computation. And also he worked on offloading the atom-based work for PME. And the idea here was kind of interesting. It was using higher order interpolation with a coarser grid. So it was to try and keep the accuracy the same, but to go ahead and then have GPU kernels for this interpolation step. And so by doing that, pushing more work from the CPU to the GPU. And also by having a coarser grid, you're reducing the parallel FFT communication. So the work here, the emphasis was really on improving communication latency. And more recent work that was done by Antti-Pekka Heinonen was just towards improving the GPU kernels that we had, and then also to offload the entire PME calculation, but that mostly benefits single node use, and then finally offloading the remaining force terms. So here the emphasis was on using GPUs more effectively. So the overlapping GPU communication and computation, the idea was to allow incremental results from a single grid to be processed on the CPU before the grid finishes on the GPU. So as the GPU was finishing work, it was streaming that to the CPU and then allowing the CPU to go ahead and poll when work was, when results were finally available and it could launch into its integration calculation. And so Jim showed you these plots as well, but I guess I can skip over these and not really recap these. But showing the projections plots of the benefit of this overlapping. I want to show you a few of Antti-Pekka's contributions here too. So he did some deep work on rewriting most notably rewriting the non-bonded GPU kernel to introduce a second layer of sorting so that he took the patches, but then within each patch he applied this recursive bisection to be able to find groups of 32 atoms apiece, so completely fill warps in kind of a spatially compact manner. And so then to be able to calculate across these 32 by 32 tiles, and to do so in a manner that allowed him to make use of Newton's third law so that he could go ahead and update forces on both Fi and Fj without collision here. And so all of these were improvements over the original kernels. And a lot more work was pushed to the GPU too. For instance, the neighbor list sorting that had to be done. And so all of these improvements made us more competitive there on Maxwell. And so here we're showing the big performance improvement going from NAMD 2.11 to NAMD 2.12 using these non-bonded kernels. And he further did some more work to basically implement the bonded forces also on the GPU and offload those. And again, basically this is giving us a performance improvement by, again, reducing the CPU workload. And so it's not that the bonded work is that much in terms of what the GPU is calculating, but taking it off of the CPU is a huge performance improvement. Because supercomputers have now been increasing in their GPU to CPU ratio. If we think about Blue Waters and Titan being basically 1 GPU per 16 cores of CPU, but now we're moving into something with Summit that has 6 voltas for 42 cores of IBM Power 9, and we only have 7 cores supporting each volta. And so that's really punishing us for any work that's being left on the CPU. On top of this now, NVIDIA just released the DGX2, which is even more extreme. This works out to be maybe 3.5 CPU cores per GPU in a highly optimized platform that has 16 voltage GPUs and high performance switching that essentially makes all of the memory on the GPUs effectively uniformly accessible. So now, with these improvements in the NAMD kernels, we've gotten a little bit of improvement with scaling across multiple GPUs. For NAMD 2.12, we were essentially flat in scaling something. Here I'm showing the STMV, which has 1 million atoms in it. And so because we are so constrained by everything running on the CPU, no matter how many extra GPUs we add, we're not getting performance improvement there, and we're getting just a little bit better performance improvement there with NAMD 2.13, which is offloading all of the force calculation. Well, what's left after the force calculation has been offloaded? Well, computationally, it's just that CPU integrator. It's 1% of the total flops here that's causing the bottleneck. So if we take a look here at profiling from the NVIDIA Insight Systems Profiler, we see a kind of a zoom in on just a single time step where you are seeing on the first two lines just 2 of the 28 CPU cores and the work that's scheduled there, and the instrumentation that I've done with a NVTX to show off the parts of the integrator. And then if you take a look at the bottom, you can see the CUDA kernels that are running down below. And we see there in different streams, we have the non-bonded forces being run as a single kernel call, the bonded forces, and then the PME work is split into a few different kernels. But overall, the GPU is not really being kept busy because you can see that there's a vacant spot there to the right of that and also to the left. And also there's a great deal of communication that's being done with the bonded kernel in particular. So if we blow up...
By communication, GPU-CPU communication, or right?
Yeah, host device communication, yeah. And so this is really just running on a single node, and so 1 Volta and 28 CPU cores. And so if we blow up on what little overlap of the non-bonded force kernel that we have with the integrator, we see that there's just too much CPU work with these 2200 patches scheduled across 28 cores. And so if we blow up further here, we can see that the patches each are running sequentially within 1 core. And the CPU integrator work is mostly data parallel with a few, with a few issues. So we do use double precision for the positions, velocities, and forces. And the data layout right now is in an array of structures form, which is not well suited to vectorization. Each NAMD patch runs its integrator in a separate user-level thread. And this was interesting. This was a design choice back in the 90s to make the source code more accessible, back when people were interested in doing research in integration methods. And but the problem is that the benefit from vectorization here is reduced because you really are only looping over maybe 200 to 600 atoms at a time. And then there are too many exceptional cases all handled within the same code path. So you've got all these exceptions that come in from, whether or not the simulation is using fixed atoms, or whether you're supporting an advanced force field that uses pseudo-atom particles. And furthermore, the code's not really that well optimized because you're testing a lot of conditionals for these simulation options and even rare events too, like whether I'm outputting my trajectories in this step. And you're doing this every single time step. So in addition, the communication, there's additional communication required because you've got to send reductions for kinetic energies and virial, and this stuff is calculated every single step, and then it's averaged. You receive this broadcasted periodic cell rescaling when simulating constant pressure. And there are also a few core algorithms that are have highly sequential parts, and so it really has reduced data parallelism in it. The two big ones for us are the rigid bond constraints, which basically uses this successive relaxation method that's done over each hydrogen group, which is just like a cluster of a heavy atom bonded to its hydrogen atoms. And then the random number generator is using a scheme right now that's pretty robust, but it's a rejection-oriented scheme where it's trying to generate random numbers and then trying to see whether or not all these are acceptable random numbers for a Gaussian distribution. And so all of these are things that won't even port well to a GPU without changing the underlying algorithms. So we've been pursuing strategies for overcoming the CPU bottlenecks, and the first strategy has been to revise the data structures so that making the data structures more amenable to CPU vectorization, so converting the atom data structure from an array of structures form into a vector-friendly structure of arrays form. We've also been investigating improved algorithms that are more amenable for CPU vectorization, replacing the non-vectorizing random number generator code with a vectorized version, and replacing the rigid bond constraints algorithm with one that is more capable of exploiting fine-grained parallelism. All this work is being done towards being able to offload the integrator to the GPU. The main challenge here is still aggregating the patch data and then use appropriate vectorized algorithms and maybe even adapt the CU-RAND library from NVIDIA for the Gaussian random numbers. However, the big goal that we're looking at is to develop a GPU-based NAMD. So in this, a GPU-based NAMD would basically be using CPU primarily to manage the GPU kernel launching, and for communication. So the CPU prepares and aggregates the data structures for the GPU, and Churn++ would handle the communication off node. And then having a GPU-based NAMD would reduce the overhead of the host-to-device memory transfers that I showed you, so that the data would live on the GPU. We would think more in terms of having clusters of patches then, and the communication would really be the edge patches for the force calculation, and then whenever we need to do atom migration between nodes. So what this will involve is designing new data structures that are capable of GPU or CPU vectorization. So this is really a major refactor of the code. And the kernel-based design, so we would also want to create a kernel-based design with consistent interfaces across GPU and CPU so that we can basically fall back to kernels on the CPU, and that would allow us to continue to support Blue Waters and Titan in older architectures. So this was my concluding slide from my GTC version of the talk. Really what I wanted to point out here, some of the take-home messages, are that the balance between the CPU and GPU computational capability keeps shifting to favor the GPU, so that the 1% workload from 10 years ago is now 60% or more in wall clock time. And any past code that has attempted to load balance work between CPU and GPU is today likely to be CPU bound. And furthermore, that the best utilization of the GPU might require keeping all the data on the GPU, motivating us to turn a previously CPU-based code using the GPU as an accelerator into a GPU-based code using the CPU as kernel management and communication coprocessor. But I want to follow up now with a slide on what will Charm++'s role be for multi-GPU NAMD. And for the single node multi-GPU case, with everything running on CPU-managed GPUs, right now, NAMD's use of Charm++ doesn't have anything to do. And the NAMD patches are non-migratable. So even right now, not only do we get no benefit from load balancing now on a single node multi-GPU case, the load balancer is actually taking extra time away from the rest of the calculation. So it's basically a performance impediment now. Now for the multi-node multi-GPU case, Charm++ handles internode communication, of course, but the load balancing is still ineffective until Charm++ understands more of the GPU work. And so that's our hope, is that Charm++ will offer ways to be able to access the GPU work in more of a way that it's done before with supporting CPUs. Charm++ could also help us make use of improvements to device communication, like helping us to take advantage of NVIDIA's NVLink connection between GPUs. So that's my presentation.
So first, a pejorative comment. It seems like we've moved NAMD from a homogeneous to a heterogeneous to now, again, a homogeneous program where that it's all on the GPUs and the GPU calculations essentially homogeneous. And indeed, if the GPUs could ever talk to the network, wouldn't need the CPU at all, and it'd be completely running on the GPUs.
Right.
This does not seem like how things are going forward. Say from our keynote. How do you?
Well, I mean, if the hardware design goes that direction, I mean, I could see, a whole bunch of DGX2s that are using NVLink or something like it to calculate, between nodes as well. I mean, where does that, why wouldn't we want to be able to run well on that kind of architecture? So, but I think that with the right designing data structures that can actually be mapped to GPUs or to highly vectorized CPUs as well, that then you can basically swap out kernels depending on what machine architecture that you're trying to run on at the time. So I see ways to be able to support either homogeneous or heterogeneous platforms, by the right software design.
So I think the unified memory things might actually make it more portable across homogeneous and heterogeneous and CPU and GPU things, because you would not do all this explicit data movement. So that might help there. The question-wise, I had one question. You said something about one single node issue. The load balancer actually causes performance impediment.
Right.
Is that true?
Well, right now, the only thing that we're load balancing with Charm++ is the force calculation.
I understand,
and so with the single node multi-GPU paradigm, we've moved all of the force calculation to the GPU. And Charm++ doesn't understand the GPU calculation. It isn't acquiring good timings, and it doesn't really have a way of doing anything to load balance what's there.
Correct, but in what way does it cause a performance impediment?
Because there's a lot of data structures that end up getting rebuilt. Jim mentioned that there's all of these, the proxy tree. So yeah.
Okay, I see. Yep, got it.